Well, this is the final live session of group theory in mathematics. And we'll be looking at applications of the group. So the first 3 weeks were really a primer that helped led us to the definition of what a group is. And now in this last week, what we looked at is different applications, kind of a survey of the vast range that group theory has in mathematics in general. And so ultimately, I know that there was a lot of new and strange and funny content thrown at you in this class. It's probably mathematics that you weren't entirely sure at times, what to deal with. And so I'm glad that you all got to come along. This is the first time I've taught this class. There's Cordelia. And so the goal really of this last week, what was, if you were able to master this stuff and do the exercises, that's great. But really is enlightening and giving you a new perspective on what mathematics really is at its core. That's kind of the goal of this last unit. So don't be too concerned about mastering all the content. Don't be too concerned about being able to solve all the problems, but rather just try to enjoy this new perspective of mathematics, enjoy this new side that you haven't been able to see before of mathematics, and have fun with it. Enjoy the new level of abstraction that isn't often available to you. So today we'll do the cancellation laws, and we'll talk about some linear equations as well. We'll look at group tables. Those are pretty fun. And then end with permutation groups and the cyclic groups as two specific kinds of groups that have pretty common application. And we'll try to also go back to previous examples that we've talked about throughout the course so that you can kind of tie together some things that you've been learning. So a group has cancellation laws. And what does cancellation really mean? So cancellation has to do with equations. In other words, if we're going to say that two things are equivalent to each other on both sides of an equation, then if one of those elements is common to both sides, then the extraneous one is also they're going to be equal to each other. You can't have different things on both sides of an equation. And so you can cancel things on the left and you can cancel things on the right. Now the symbols and the way that it's denoted here makes it look a little bit more complicated than it actually is. So what I'm going to do is go to the whiteboard, show you some examples, and to simplify something that is intuitive to you all. So with cancellation laws, suppose I had that 2 plus 3 is equal to 2 plus 3. And this is pretty common sense. In other words, I just wrote down the same exact thing on both sides of the equation, and then we expect that to be true because I just copied what was on the left and then I did it on the right. Now, here's what's a little bit different. What if I hadn't shown you this? What if I first showed you this? 2 plus 3 is equal to 2 plus x. And then if I were to ask you, okay, well then what is the value of x? And of course, the value of x would be 3. But how do we really know that? And so this is where that left cancellation law comes in. We have the element 2 on both sides of the equation. And notice that that is the same. And then we have another element that's interacting with the 2. What the cancellation law is saying is that if we have this same element here, then this is going to imply, if these two things are equal, that the other two elements are actually the same thing. So that x is equal to 3. And so this is really what's at the very foundation of what it means to solve an equation. You'll see that cancellation laws and the linear equations go hand in hand in that way. Is that we use the cancellation law as the primary method to solve linear equations and to find those solutions. So we don't just cancel stuff that's on the left. We can also cancel things that occur on the right. So if I had instead said 2 plus 3 is equal to y plus 3. Well, again, we have the common element of 3. And that is the same on both the right sides of this equation. And we have two leftover elements, the 2 and the y. And so what the right cancellation law tells us is we can cancel the common elements on the right side in a group and then show that the other two elements are actually equal to each other. And so in this case, y would be equal to 2. So this is the left cancellation law. This is the right cancellation law. So let's take a look at why this is the case, why we can do any of this. If I had the element x and I multiplied it against a, and notice that I'm using a generic binary operation now. I don't want to restrict myself to a particular example because I'm trying to make a general statement. And then I also have x again, so I'm repeating that element. And then now this time I'm going to have a different element. I want to know if this is going to cancel. In other words, can I cancel the x's on the left side to show that a is equal to b? So even though we're not using numbers anymore, we have the same kind of setup. We have a left element that is the same. And then we have two other elements. And we're going to cancel the same elements from the left side and then simply show that the other two elements are the same. And so here's how we can do that. We start with the original equation, x star a is equal to x star b. And now, what we do know is that we have a group. And since these are all elements of a group, that means they have inverses. So the element x has an inverse x. And that comes from that third group axiom. And so we have that. We can call it x inverse is the inverse of my element x. Because this is a group, we are guaranteed to have both of these elements. So what I'm going to do is I'm going to multiply the inverse of x on the left side of the equation on both sides. So I have the inverse star, and then here's my x star a that I had before. And then I'm going to take the inverse. And then here's my x star b from before. So now there is the associative property of the binary operation. And so the associative property lets us shift around the parentheses. So instead of them being where they are now, I can move them to the first two elements. So I'll put x inverse star x together and then have the a outside. And over here, I can shift it over. So there's x inverse star x star b on the outside. And so that is the associative property. Now that we've done that, we can simplify this. So remember by definition that the inverse, when you interact an element with its inverse together, you get back to the identity. So x inverse star x would just be whatever the identity is for the group. And then we still have a. And then again, we have the identity star b. So that's just simplifying. And then an identity is the element that if you were to interact any other element with it, you simply get back the element. So the identity together with a is a, and the identity together with b is b. So that is by the identity. And look at that. We end up with the conclusion that a is equal to b. And we get that from this equation right here. And so whenever you are in a group, which is what's going to happen when you go on and take your high school algebra classes or whatnot, and you will use this cancellation law without really realizing it. They'll call it different things. They'll have different visual tricks for it. But at the bottom line is that this is really what we're taking advantage of. We're taking advantage of cancellation laws from groups. All good? Awesome. Okay. So then we have linear equations. Linear equations is basically the continuation of the idea of that you can cancel things using the inverse elements. And so if you have a group, then a linear equation is going to have a unique solution. What this means is you can't have a linear equation that's going to come up with multiple solutions. If you have a linear equation, it's only going to have exactly one solution. And we can show that we have a solution. So in general, if I had an equation, A star x is equal to B, and then the way I would solve this equation is I need to find the element x such that when I interact it with A, I get the element B. Now there's different ways I could do this, but the most straightforward way is to just simply use the group axioms again. I know that to isolate this x, I just multiply the left by the inverse of A. So the inverse of A, and we still have the A star x. And then we have to do it to both sides of our equation. So we have A inverse B. Now by the associative property, so this is our inverses in versus. And by the associative property, we can move the parentheses over. So it's around the A inverse and the A first. And we don't really need to change anything over here. So that is the associative property. And then the inverse again will become the identity. When interacting an element with its inverse goes to the identity. So we have E star x, and we still have A inverse star B over here. So that's simplifying. And then the identity with any element is just going to give back the element. So I have x is A inverse star B. So this element right here is the solution to the equation A star x is equal to B. And that is by what we know about identities. And we know that this is a unique solution. And here's how we know it's unique. Because what we're going to do is we're going to pretend like there's another solution. So let's say that x1 and x2 are both solutions to this equation. Well, that means that A star x1 is B, and A star x2 is also B. And since they're both equal to B, we can put them together in the middle. So A star x1 is equal to A star x2. But we just showed when we were doing that left cancellation law, take a look, we got the same exact element on both sides, and we're in a group. So we can cancel these, and this is going to imply that x1 and x2 are actually the same. So we wanted different solutions, but we ended up showing that assuming there's more than one solution leads to the conclusion that there can only be one solution. And that's how we know that linear equations only have one solution. Their solutions are unique. Does that make sense? Okay. So group tables is a continuation of essentially what we were doing in the previous week when we were doing the binary operation tables. And now all we're doing is we're creating binary operation tables that satisfy the group axioms. And so that's all a group table is. A group table is a binary operation table that satisfies the three group axioms. And the way that you can construct these things, the first thing to do is to simply list the elements in your group. Then what you'll want to do is create a blank table And you can fill the first row and the first column by the identity axiom. It's just going to spit back the same thing with the identity. And then the harder part is to fill in the rest of the table such that each element appears exactly once in each row and column. So if you've played like Sudoku, then you can't have 2 9s in the same box, or you can't have 2 2s in the same row. And in a similar way, we're going to find that we can't have 2 of the same element in one row or one column, because that would defy group theory, or the group axioms. So let's take a look at how we construct some of these. Let's start first with something we call the trivial group. And the trivial group is the group that contains exactly one element. So it's a little bit boring because you've only got one element in your group. And that one element, what do you think that has to be? Throw it in the chat. So if you have a group with only one element, which you know about the axioms, what element must the single element be? Yes, the identity element. If we're only going to be allowed to have one element, and every single group has to have an identity, well, there you go. So the identity takes up that one element space. So we have, whoops. So we have that the trivial group is the identity element all by itself. And so we can make the group table for the trivial group. So here's the binary operation, and we list the elements. So there's only one element, so it's just E. And so what is the only possible combination? Well, the only possible combination is E star E. And what does that have to be? E star E is going to be E, just the identity. And so right here, that is the trivial group expressed as a table. Now that's pretty boring because there's only one element. So let's now bump it up to 2 elements and see what happens. So now we want a group with 2 elements. So we have to have the identity in there. And what we do is we just give an arbitrary label to the other element. So when we list these out, we got the identity, we have A, and the identity and A. So let's fill out this table. Go ahead and put this in the chat. So E times E, what does that have to be? Good, that has to be E. E is the identity, don't forget that. So in light of that, what does E star A have to be if E is the identity? Good, it's going to be A. And then now let's fill in this bottom row. So A star E, what is that going to be? It's going to be A. And then A star A, what does that have to be? Okay, we have a vote for A. Here's my question to you. We have identity. What's the inverse? So we need to have an inverse for every single element. So we only have 2 total elements. So the inverse of A has to be A. And what do we know about multiplying an element together with its inverse? Which special element do we get out of that? Yes, the identity. The inverse times itself is going to be identity, or rather an element and its inverse. So we get this nice little symmetric pattern where we have EA at top and then AE down below. So this is what the finite group of order 2 looks like. Notice that each element occurs once per row and per column. If I would have put an A right there, then I would have had 2 A's on that row and 2 A's on that column, and it wouldn't have been a group anymore. So we needed to make that the identity. Does that make sense? And Cordio says that pattern looks a bit like that of an identity matrix. Yes, it does. Very good. Let's bump it up to the next one. So 3 elements now. So like the pattern goes, we have the identity. We're going to have 2 arbitrary elements, A and B. Okay, so let's construct this group table. And again, we're going to do it piece by piece. So let's first consider the first row here. So the first row is going to be the identity multiplied by these elements. So can you type in the chat what these first 3 elements are in that first row? Good. E, A, and B. Excellent. We have E, A, and B. Now, again, down this first column, because that's with the identity, what do we know those elements are going to be from the top down? Exactly. It's the same exact thing, just E, A, and B. Okay, so that leaves just these 4 spots in the middle here. So the first thing we want to check is what is going to be the inverse of the inverses. So now how many elements do we have again? Right, so we have 3 total elements. Now, one of those elements is taken up by the identity. So how many leftover elements do we have? Right, we have 2 leftover elements, and those are A and B. So that means what element is left over to be the inverse of A? Yes, so A and B are inverses. Because they're all they've got. So that means A star B is going to be what? If A and B are inverses, and if you have an element multiplied by its inverse, exactly, you get back to the identity. And so in the same way, we know that B star A is going to be what? Yes, excellent. So the identity is going to show up here, and the identity is going to show up here, because that's A star B and B star A. So notice we don't really have to do any more computations over here for the rest, because what element is missing from the rows and columns on those 2 spots? Yeah, we're missing A and B. So which element's going to go here in the center? Right. And we have to put B here because we are only allowed to have the element up here once in each row and column. So I can't put A because we already have an A in that row and column. So then what's left over in the bottom corner here? A, exactly. Does that make sense? So this is the finite group of order 3. So you can really see this is very fun to do. It's kind of like a game to fill out these things, to see the symmetry, to see the structure. Now, here's a really fun thing to look at. I'm going to draw a line. And if I were to make this blue dashed line through here, notice that it's a mirror image, that A to A, B to B, E and E. And so not only is this a group table, but it is an abelian group. This is abelian because this binary operation is commutative. In other words, A star B is equal to B, or sorry, A star B is equal to B star A. And no matter what combination you have, X star Y will give you the same thing as Y star X. So this is an abelian group as well. Okay, do you guys want to do the finite group of order 4 next? Because there's two possibilities. There's two different ways you can fill out the group of order 4. So here's the identity, and we have 3 extra elements. So here's E, A, B, and C. E, A, B, and C. Okay, so this first one that we're going to do, it's called the 4 group, where this capital V comes from the German, which the letter or the word for 4 in German is vier, so that's why it's a V. Okay, what's the first row going to be? Good, yeah, E, A, B, C, and same thing for the first row or a column. So E, A, B, C. Now, here is where it's a little bit interesting. We have 2 options. And so when you have the 4 group, the 4 group is the one in which you make every single element its own inverse. So A is its own inverse, B is its own inverse, and C is its own inverse. So in that way, notice how we get the identity element once on every single row and every single column. And then you just use process of elimination to fill out the rest. So what goes here with A star B? So the question is, can I put B here? No, I can't. So the only other option left is C, like Miles put in the chat. Okay, and so what does that mean? This last element here is going to be in that row? Yep, it's going to be B. Okay, so what is going to be B star A? And then B star C? Yep. And then we can fill in these bottom ones. So what about C star A? Good, and then C star B? Excellent. So if we take a look at this, let's see if this group is also abelian. I'm going to make that diagonal line through. Well, there's symmetry because that A goes to A, B goes to B, C goes to C, C also goes to C here, B goes to B, and A goes to A. So this is, the 4 group is abelian. Make sense? Now what I'm going to do is I'm going to present the other group with slightly more familiar symbols. And I think this will really click. So we're going to take 0, 1, 2, and 3. And we're going to do addition mod 4. So 0, 1, 2, 3. 0, 1, 2, and 3. What is 0 plus 0? Right, and so, well, 0 is the identity, so what's this first row going to be? Right, 0, 1, 2, 3, and then 0, 1, 2, 3 down the first row as well. Okay, so now let's fill this out using arithmetic, right? So what's 1 plus 1? Good, and then 1 plus 2 is 3, and 1 plus 3 is 4. Now here's the thing, we're in mod 4. So that means 4, any multiple of 4 is actually a 0. So we go back to the identity element. All right. What is this? What 3 elements are going to show up in that row? So 2 plus 1 is, yep, 3. Now that's really close. So we have 3, 0. But then once we go back to 0, we just keep counting. We start the counting over then. So then 0 goes then to 1 if we add 1. So 2 plus 3 is 5. And then we subtract 4 away from that and see that what's remainder is 1. So then that's what would be right here. So then for the very last row, what's the last row going to be? 3, 0, because 3 plus 1 is 4. But then if you take away 4, you get a remainder of 0. And then 3 plus 2 is 5. 5 divided by 4 has a remainder of 1. And then 3 plus 3 is 6. And 6 divided by 4 has a remainder of 2. So this is what we call the integers mod 4. So there are two groups. Notice that they're different. They have a different structure because here the identity doesn't go down the diagonal like it did over here. So over here, what goes down the diagonal is 0, 2, 0, 2. And yes, this is still abelian though, because 1 goes to 1, 2, 2, the 3, the 3, the 3, the 3, and the identity to identity, and 1 to 1. So this is also abelian. And that makes sense. We expect the counting numbers with addition to be abelian because addition, the operation plus, is a commutative operation. So it's a little less clear when we use the more abstract notation, but when we use something more familiar, we can start to see where these structures come from. All good? Awesome. So permutation groups. This is a lot of fun to do when you actually have a physical object. It's not as fun to do in your imagination. So what happens is algebra and symmetry are closely related in the sense that the different ways you can manipulate shapes along their lines of symmetry, you can turn those things into elements as well. And so pictured on the left is a triangle with its lines of symmetry. That is, if I were to spin the triangle around one of those dotted axes, then it would just look the same. It would look like I hadn't changed the way the shape looked. And those are what the lines of symmetry are for the triangle. And so another thing I could do is I could actually rotate. I could just take the whole triangle and then rotate it, and then until it looks the same. So there are 3 different ways. I'm going to grab my pen here. There are 3 different ways you can rotate it. Row naught, row 1, and row 2. So row naught would be as if I had just left the triangle alone. I'm not going to spin it. I'm not going to do anything to it. And then row 1 is I'm going to rotate the triangle clockwise just once. So that's going to bring this down to here, this over to here, and this up to here. And it'll look the same, but I will technically have rotated it once. And so then intuitively, row 2 is going to just be doing 2 total rotations. So that's what these elements are. These are describing rotations of this triangle. And then the other elements are reflections really about the lines of symmetry here. So this line of symmetry, if I were to spin around, if I were to reflect it around that line of symmetry, then that's mu1. And if I were to reflect it about the other lines of symmetry, then I would have the other 2 reflections. So that I have in total 6 possible symmetries of this equilateral triangle that I can rotate it or I can flip it to make it look the same. And so what's actually in this table? Well, this is telling me that if I were to rotate, so if I say I did this right here, if I were to rotate my triangle twice and then flip it along this line of symmetry, then the result is the same as if I had just simply rotated along this line of symmetry over here. So if you ever have the chance to get a piece of cardboard or paper or something, cut out an equilateral triangle, and then label the 3 corners, 1, 2, and 3. And then note what happens every single time you manipulate it. So if I were to rotate it, for example, you might choose to have cut out a triangle and call this 1, call this 2, and call this 3 up here. If you were to do row 1, in other words, you were going to rotate it like that, then you would end up with the triangle looking like this, right? So the 1 would rotate up to here, like this, and the 3 would rotate down to here, and the 2 would rotate over to here. So you would obtain this element. And so permutations is simply rearranging and reorganizing your elements. And so you could call 1, 2, and 3 your elements, and then permuting it on a triangle is going to give you different kinds of permutations. And then you collect all of those permutations together. That becomes your permutation group. Make sense? And so that's why algebra is kind of obsessed with symmetry. It's because we can do lots of fun things. Another geometric shape that has a lot of symmetry to it is the square. So here's a square. If you really think about this, how many times could you rotate this clockwise? How many unique rotations could you get to have symmetry? Go ahead and put that in the chat. Right. You could rotate it once. So if I labeled this 1, 2, 3, 4, you could rotate it clockwise once, and in doing so, this would be now 1, this would be 2, this would be 3, and this would be 4. So I've rotated the square again. Now, if I were to rotate again, so this could be considered row 1. So if I were to rotate it again, clockwise, then the 1 would travel down from being in the top right to the bottom right. So 1, 2, and they would all cycle around. And then I could rotate it one more time. And now my 1 has traveled over here, and then all the rest of the sides, all the corners come around. So this could be considered the default position. So the identity, row naught. So we rotate it 0 times, and then we rotate it once to obtain this element. We rotate twice, rotate 3 times. So we have 3 different rotations, and then an identity rotation. And then if you think about it, what are the lines of symmetry here? Well, we could have a line of symmetry that comes down like this, and I could reflect a square over that. The square is also symmetric around the horizontal as well. So it has a vertical and a horizontal line of symmetry. And there are 2 more lines of symmetry. Do you guys know what those are? Yes, the diagonals. So I could have diagonal. And so when I compile all of these together, I have my set, my group. And there's going to be 8 total elements. So the light blue elements, these are the rotations. So here's my identity, row naught. And then row 1, row 2, and row 3. And then I have rotations, and we call that mu1 and mu2. And then we have diagonal lines of symmetry, which I can call delta 1 and delta 2. So these elements together form a group. So here's my question for you. This is a little bit sometimes difficult to visualize, but I think you can do it. What would be row 1? What element do you get if I do row 1 first, and then after performing that rotation row 1, I perform the diagonal delta 1. So this will be delta 1 right here. And track what happens to your square. So let me draw a square, a fresh square over here. So if we have 1, 2, 3, and 4, what's going to happen if I execute one rotation and then that diagonal? So the first thing, let's do it one step at a time. Let's first do row 1. So after row 1, what is the top right corner going to be? 1, 2, 3, or 4. Put in the chat. It's going to be 1. This is because we're rotating the entire square 90 degrees. So then the bottom right is going to be good. The bottom left is going to be, and then the top left is excellent. So now we just did row 1. So that's row 1. Now after doing row 1, let's do delta 1. So we're going to rotate about that line of symmetry, this diagonal right here. So which two corners are going to stay the same if we go through that diagonal? Yeah, 4 and 2. So these are the same. And so what happens to the other 2 corners? Yeah, they get swapped out. So instead of 1 being here, 3 is going to be up top. Instead of 3 being down here, 1 is going to be down there. Okay, so that's interesting. What single rotation could execute those 2 combined? Yeah, exactly. We could have just done, well, let me think about that. Well, row 3 would give you this right here. So it's not quite this one. If we take a look, so we would have 1. We would need to get this down. Don't forget the red ones. Don't forget that you can do rotations of symmetry about the red axes here. Do you see it? Yep. Here's move 1. This is move 1. Because if I was to reflect the square, so here's the original square, 1, 2, 3, 4. And if I were to flip it about that horizontal, then I'm swapping 1 and 4's positions, and I'm also swapping 3 and 2 positions. So I get this pattern, and that's exactly what we end up right down here. Does that make sense? So that's pretty cool. You can do arithmetic with pushing shapes around. And so symmetry, this is really, really useful. We use this to tell time. All sorts of patterns come from this: combination locks, passwords. There's a lot of different things that come from these permutation groups. And so this is a really, I think this is one of my favorite parts of algebra, is seeing the connection to geometry and seeing how you can turn an action into an element. I think that's what got me the first time. It's because you often think of a math element as like a number or something like that. When the element can be so abstract that it's an actual action that you can make. So that's really, really fun. So when you go about, think about all the different things that you might not have considered could be a mathematical element that actually might be with symmetry. So you can turn most symmetrical things into an element of some sort of a permutation group. So that's a quick overview of the permutation groups. There's so much more you could do with permutation groups. I mean, if you want to do more, there's in the exercises provided. And the solutions are also at the end of that textbook as well. All right, any questions about what's on the board? Sweet. Okay, so very last thing, cyclic groups. So I have all the stuff on the slide here just because it's definitions and whatnot, but it's not the most important thing to know. So what's the most important part is this idea that if you take an element and you repeatedly add itself to itself over and over and over and over again, or you repeatedly, whatever the binary operation is, doing the operation on a single element over and over and over again, what's going to happen? Is it going to go in circles? Is it going to take up all the elements? And so that is all addressed with cyclic groups. Cyclic groups are the study of exactly that, where you take an element and you repeatedly do the operation on that element over and over and over again until you cycle back to the original starting place. So that's why it's called a cyclic group, because it's inherently going to cycle back to itself. So that's what this really means. So this subgroup H, the A to the N, where N is an integer, that just simply means repeating over and over and over again. And then if you can actually generate all of the elements inside of your original group by repeating just one element in the binary operation over and over and over again, then we call that group cyclic. So I'll give you a good example of this. Let me grab a pen. Okay. Who here still has like an analog clock that they use to tell time, or is everything digital these days? What else? Let me grab try to draw a circle here. Oh, you have an analog clock. That's great. So let's do a 12-hour clock. So here's 12. And here would be 3. And here would be 6 and 9. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. We could have that one. Okay. So we could start at midnight. This is a cyclic group. So here's how we're going to do this. We're going to start at 12 o'clock. After 1 hour, where are we going to be at? So what we're going to do is we're going to repeatedly do the operation of adding 1 hour at a time. Okay, so what we're going to do is we're going to add 1 hour at a time and see what that generates. So let me actually move this down here. So we're going to investigate what 1 is going to generate. Okay, so if it's 12 and I add an hour of time, what time is it going to be? Yeah, we'll be at 1. Okay, so that was expected. Now, what happens if I then add another hour of time? Right, we get to 2. Now we're going to continue this pattern. So we repeatedly add again. So we're going to add another hour to 2 o'clock. And that gives us 3. Now, if I were to then add 3 or add 1 hour to 3, what do I get? Now, do you see how this is going to go all the way around the clock until we get back to midnight? So we're going to go all the way around. And I'll do this in a different color. So eventually, if we keep adding and adding 1 hour at a time, whoops, to make that a dotted line. We collect all of the elements on the clock. So here's the real question. So if I go from 5, 6, 7, 8, 9, 10, 11, 12, what happens after I add an hour to 12? Yeah, well, that looks familiar. That was all the way back here. So we're back to 1 and we don't keep listing elements in this direction. What we do instead is we simply close off our set. So this hour, so the hour 1 generates all 12 hours. And because of this, so this is the whole thing, we call 1 is a generator. And telling time, the clock is cyclic. And so really embrace that intuitive notion of being cyclic. To be cyclic simply means to cycle around. If you have a bicycle, if you look at the spokes on your bicycle wheels, each one of those spokes is like an element. And every single time it spins around, it goes in cycles. There's a cyclic group right there, where every single little bit of rotation is an element. So permutation groups, cyclic groups, all of these things go together. This is all algebra. And it's all algebra that really gets pushed under the rug, or it gets it's postponed. So symmetry is beautiful. Cyclic groups, you get linear equations from group theory. You get lines of symmetry and geometry out of group theory as an application. You get the reason why you can cancel when you do equations. All of these things come from group theory. And so group theory is this undercover, under the hood mathematics that's going on as you progress through your mathematical studies going forward. So are there any questions before we close today? There's just a very, very last progress check to do. And that this is the very last live session. So you'll have until the end of the weekend to get everything kind of finished up here. But otherwise, that's the class. It is my hope that over the last 4 weeks, at some point, something in your mind changed about mathematics, that you were exposed to something that you probably were like, why on earth is this even considered algebra? What is this? This is so weird. And hopefully it left a little rock in your foot, in your shoe, get stuck in your sock, something that doesn't, bother you too much, but you can't ignore it, a little bit of an itch. So if this changed your mind at all about mathematics, what mathematics really is, and things related to, then let me know. I'd be interested to hear. There is a place to post class reviews if you think that other students would enjoy taking this class next year. And then I'll post information about that later. But I hope you enjoyed this class. I really enjoyed teaching it. I had never been able to teach group theory before. So super, super fun. You guys were all great. I'll be around to tell everybody these if you have any last questions. But for now, that's it. Thanks so much for being a part of this class, guys.